All right, in this video, we're going to be talking about 1.4 properties of radicals. Radicals, the basic one that you all already know or should know is the square root. It goes a little bit further. We have cube roots, fourth roots, fifth roots, and so on and so on. So a couple things to note. If a so basically, okay, so like if you have something like this, the nth root of a positive number, then you can simplify it to something. It will give you something. The issue is how's the best way to explain what that property is telling you? If the nth is even and it's positive, it'll be a real number. It might not be perfectly simplified, but it'll give you a real number. If you have a radical and the nth is a odd and it's a positive, you'll get real. So you get a real number regardless if a is positive. But if it is a negative and this is a even index, this will not be a real number and not possible. If your index is odd and negative, you'll still get a real number. So I guess really the moral of this is the index can be anything and the number can be anything. You'll get a real number except if the index is in and it's a negative. Now, the terminology here, let's see, we'll call this an I, we'll call this a letter, and we'll call this an E. All right, this guy right here is the radical sign. This is what we talk about when we're talking about radicals. It looks like a square root. This I here, the little number, that's what I call the index. The number that's above the x is still the exponent. But this can be written as x as e over I. That's how I remember it, E over I. So a radical can actually be written as a exponent in a fraction form. And this is kind of what I was telling you in 1.2 that this will eventually come into your lecture. So that's pretty much what a radical is, kind of broken down in general. When it talks about perfect powers, it just means that it goes into it evenly. So like the square root of 4 is 2. The square root of x squared is just x, and the radical goes away. Same thing if I got the cube root of 8, that's 2, and the cube root of x cubed, that's x. So again, the perfect cube, perfect square, perfect fourth, whatever, a perfect power basically means that it evenly turns into a nice, pretty number without a radical. We do want it in its simplest form. So if it can be simplified, we must. And then we, of course, we have some properties to go with this. So the properties are, if I have multiplication going on inside of a radical, I can separate it. But it's even bigger is if I actually am multiplying two radicals and they have the same index, I can put it in as one big square root. That might help me simplify the question a lot easier. So you can go both ways here. Same concept with multiplication. I can separate it, or I can put it together. And again, that might make the fraction easier to simplify if I put these two things together. And then this last one here is if I have a radical and another radical, this is like a power to a power situation. So this would be the same concept if I, not an n, let's try a. It's the same concept if I do m times n to this radical. So meaning if I take like the cube, like for example, If I take the cube root of the square root of x, that's the same thing as the sixth root of x, because there's the radical that doesn't have a number is like an imaginary 2 there. We don't necessarily write it, but we know there's a 2 to represent the square. Notice that's multiplication division. We do not have rules that apply to addition. So there's a caution in your book. This is not a true statement, right? And you can check it, right? 9 plus 16. 9 plus 16 is 25. The square root of 25 is 5. Square root of 9 is 3. So like, for instance, 9 plus 16. 6, sorry. This will give you 25, which is 5. This is 3 plus 4, which is 7. So this does not work. So don't get tripped up on addition and subtraction. It's only properties for multiplication and division. There is something called rationalizing. I'll do that when we get into the exercises. It'll be easier that way. And then I've already talked about rational numbers as an exponent. This right here is the easiest concept to write it as e over I. So whatever the inside number goes on the numerator, the index there goes as the denominator. And that seems to be pretty much of the gist of this section. So let's get into some exercises so that you are a little bit more comfortable with the knowledge. All right, so I'm going to be on page 50 on exercise 1. So this one just says negative square root of 9. In this set, it just says to evaluate the following radicals. So in here, again, we treat the square root as a grouping, so we deal with that first. So the negative will just ride. The square root of 9 is 3. So therefore, the answer would be negative 3. So let's look at number 2. The cube root of negative 27. So to kind of go back here, the way you're able to get 3 is 3 times 3 gives you 9. So it takes 2 numbers to come out as one solid. What you're trying to do here is think of one number times itself that would give you negative 27. So I need 3 numbers here. And hopefully you're going, well, maybe negative 3. And so negative 3 times negative 3 is 9, times negative 3 is negative 27. So in this case, the answer is negative 3. Let's look at number 3, square root of negative 25. So that spiel I had at the very beginning of this lesson is where it's very important. Notice a odd index, positive or negative, doesn't matter, I get a real number. An even index, remember, if there's no number there, there's an imaginary 2. And with an even index, I cannot have a negative inside what we call the radicand. So what we'll say is this is not real. All right, let's look at another one. Let's look at number 11. Number 11 is the cube root of negative 27 over 125. So this one might be a little bit harder to see. So I know with a odd index and a negative, my answer will always come out negative. So I'm actually going to pull that negative out. And then I'm going to separate these two as two separate things, especially since I can't simplify it. This is the cube root of 27, and this is the cube root of 125. So when I look at this, 3 numbers that give me 27 would be 3, 3, 3. So that means that this would be negative 3 on top. Notice that's a perfect power, so the radical went away. And then when I look at this one, 5 times 5 is 25 times another 5 gives me 125. So that's going to give me 5. So the final answer here is negative 3/5. So when talking about perfect powers, again, notice all of these came out as nice numbers without a radical. It's not always the case. All right, let's look at number 12. We have the square root of 25 over 121. Again, I'm going to separate these as two separate things. So the square root of 25 over the square root of 121. Square root of 25, I just need two things this time, which would be 5 times 5, so that would be 5. Two things that multiply to 121 would be 11 times 11, so in this case, that would be 5/11. Perfect squares there. All right, last one in this group, so let's look at number 16. So it's going to be the fourth root of the square root of 16 minus the cube root of negative 27 plus the square root of 81. So again, in grouping, I need to work within the most inner groups first. So the fourth root will just hang out here. And I got to do each one of these as its own separate grouping. So the square root of 16 is 4 times 4, so that means that's going to be a perfect square. Minus the cube root of negative 27 is negative 3, negative 3, negative 3, so that's going to be a negative 3 that comes out. Plus the square root of 81, that's going to be 9 times 9, so that's going to be 9. So all those are perfect powers. And then I keep on working this out. I see that two negatives make a positive. So 4 plus 3 gives me 7. 7 plus 9 is 16. Now I got to ask myself, fourth root of 16. So that's going to be what number times itself 4 times will give me 16. So I'm going to start off with 2. 2 times 2 is 4. 2 times 4 is 8. 2 times 8 is 16. So 2 is my answer there. All right, let's go into the next set of questions. So I'm going to look at number 19. In this set, it says simplify the following radical expression. So this time we're not going to get perfect numbers per se. We're going to have some letters involved in this as well. So we get the square root of 9x squared. When you're dealing with numbers, treat it the same way. What number times itself 2 times can give me 9, and I see that it's a 3. So square root of 9 is a perfect square. When it comes to letters, best way to approach this is to divide the exponent by the index. So 2 divided by 2 is 1. So therefore, you just have x to the 1 power, but we don't write that, so it's just 3x. Now we have number 20. So this would be 3, the cube root of negative 8x to the 6y ninth. So let's apply that again. This time I'm looking for a number times itself 3 times to give me negative 8. So in this case, that's negative 2, negative 2, negative 2. That's 4, negative 8, so that's true. And then I'm going to divide. So 3 goes into 6 2 times. 3 goes into 9 3 times. Best way to approach those exponents with letters. All right, let's look at number 22. Number 22 is the square root of 2x to the 6th y. So now we're getting into things that aren't so pretty. I don't know two things that can multiply to 2. So therefore, 2 is what we call a leftover notice, non-perfect square. So that means I'm going to still have a radical sign. So notice every answer we've done up to this point, the radicals disappeared. But now, starting on 22 here, we're dealing with things that are not perfect squares. And when they're not perfect squares, they must stay inside the radical. So the 2 is unable to simplify, so I don't go any further. Then I'm going to take that index of 2 and I'm going to divide. So 2 goes into 6 3 times. If it goes into it perfectly, notice it came out of the radical. It's no longer an x inside the radical. Now this next one, 2 does not go into 1. Remember, there's like an imaginary 1 right here. So with that being that I cannot simplify y any further, so it must stay inside the radical. So if something can be simplified, take it out of the radical. If it cannot be simplified, you leave it inside the radical. Right? That's a big thing that students will get tricked up on, especially after going through all these examples and not having radical in our final answer. But let's do quite a bit more so that we're getting more comfortable with it. Let's look at number 24. I have the square root of x squared over 4x to the 4th y to the 6th. Before applying the square root, you do want to simplify your radicand itself. Basically get it down to one letter. So this is going to be the stuff that we worked on in the last video. So I'm going to separate my coefficients, my x's and my y's. So in this case, I still got a 4 on the bottom. I can subtract. So this gives me 2 minus 4. And then the 6 is going to stay on the bottom because there is no y. So that gives me 2 minus 4 is negative 2. So that means that this then has to go back to the bottom. Now check this out. If there's nothing left in the numerator, there's still 1. Right? If everything ends up going to the bottom of the fraction or the denominator, you're still left with a 1 as a numerator. All right, so now I'm going to separate these as two separate problems. So this is the square root of 1 over the square root of 4x squared y 6. Now I'm going to simplify these independently. Square root of 1 is 1 because 1 times 1 is 1. Square root of 4 would be 2 because 2 times 2 is 4. 2 goes into 2 one time evenly, and then 2 goes into 6 3 times evenly. Notice I no longer have a radical because everything was a perfect square. Sorry, I kind of went up like that, but I was trying to make sure I had plenty of room. All right, let's do another example there. Look at number 26. So it looks like it's the cube root of negative 125 x to the 12th, y to the 9th. All right, so same process, three numbers that multiply to negative 125. Let's try 5. So negative 5 times negative 5 is positive 25 times negative 5 again would get me that negative 25. 3 goes into 12 4 times. And then 3 goes into 9 3 times. So therefore, that it will be your answer again. Everything came out evenly, so it's no radicals left. Let's look at number 28. This would be the cube root of 81m to the 4th n to the 7th. So again, I look at 81. I try to think of three numbers that multiply to 81. I want to instantly think 4, but 4 times 4 is 16 is 64. So 5 would go to 125. Oh, okay. So I don't think I have enough numbers, but I think I can go to 4. So 3 times 3 would be 9. So I think 3 times 3 times 3 times 3 would give me 81, but I can only handle 3 of them because it's a cube root. So this group of 3 would come out as one single 3, and then that would be your leftover inside the radical. So I was able to pull a 3 out, but a 3 had to remain in because, again, for a cube root, I need 3 of them to come out as one nice number. 3 then goes into 4 one time with the remainder of 1. So 3 goes into 4 once with the remainder of 1. Then 3 goes into 7 2 times. Forgot the index of 3 there. 2 times with a remainder of 1. So therefore, this would be your final answer. So again, working it that way, keeping the perfect stuff on the outside, any leftovers stay on the inside. All right, let's do another set here. Let's look at number 32. This is negative square root of 3a cubed divided by square root of 6a. All right, so I'm going to make this one gigantic one to simplify it first. I told you earlier that it could go both ways to help you simplify. You just never know what's going to help better. And then when I'm simplifying this, again, I'm going to simplify it by my coefficients and my letters. So 3, 6 actually simplifies down to 1/2. And then a would be a 3 minus 1. So remember, there's an imaginary 1 there. So that's going to give me the square root. I don't necessarily need the 1, so that's going to be a squared over 2. All right, now I'm going to separate these back so I can work them out as two independent questions. So notice it's a lot cleaner than starting there. When I work this out, I see that the square root of a squared is a, but the square root of 2 does not work out. And if you go back to the directions for this set, it says simplify the following radicals by rationalizing the denominator. So what happens is when we are left with a radical in the denominator, that cannot happen. So we have to figure out what do we have to multiply to make it a perfect power. So in this case, since it's just a square, root, I just need two numbers. So I can actually just multiply by itself because then that would give me 2 to make it a perfect square. But again, just like in the last videos, what I do on the denominator, I must do in the numerator. So in this case, and I think I lost that negative down the road, so let's bring that back. So this will now give me negative a square root of 2. That can happen, so just kind of follow your work. And then the square root of 2 times the square root of 2 gives me the square root of 4, which is 2. So the whole point of multiplying that was to get rid of that radical sign. So you get a nice clean fraction. Let's do that again. So let's do number 36 this time. 36 is 5 over 6 minus square root of 5. So that was actually an easier one. When you are left with what we call a binomial as the denominator, meaning it is something with two terms and where terms are separated by addition and subtraction, you have to multiply by what we call the conjugate. All right, so the conjugate is the exact same binomial. We just change the sign in the middle. So I'm going to take this guy and I'm going to multiply by the exact same thing, but with a positive. But of course, if I do it to one side, I must do it to the other side. Now, the whole purpose of doing this, and I think it's shown in your book, but really and truly on the numerator side, all you have to do is just multiply the first term and last term of this full process when distributing two binomials together. And the reason is because this actually plays out as the difference of squares. So a plus b times a minus b is the same thing as a squared minus b squared. So instead of having to FOIL it 4 times, I can really just square the first number, square the last number, and then have a subtraction sign in between. If you can remember this process on the bottom, you'll save yourself a lot of work. So 6 times 6 is 36 minus square root of 5 times square root of 5 will just be 5. Just like up here, the purpose of multiplying two radicals that are exactly the same is to get a perfect square. Because again, square root of 5 times square root of 5 gives me the square root of 25. So that's the purpose. So now there's no longer a radical on the bottom. Now the top half doesn't have any special rules. You'll have to distribute or multiply whatever is up there with the conjugate of the denominator. So in this case, 5 times 6 is 30. And then 5 times square root of 5 will just be 5 square root of 5. So do watch out for that. A coefficient times a radical, you cannot actually multiply them. So you have to write them out as is. Now we can multiply radicals to radicals as long as they're the same index from our properties, but we cannot multiply coefficients to radicals. So I'm going to clean this up. 36 minus 5 does end up being 31. And that's it. There are some books that do separate these as two separate fractions. And they kind of do that to help you with dealing with quadratics and getting you to the point of using the quadratic formula. When we get to that point, you'll see me separate them for you like that. But really and truly, this is just as clean as separating them as well. All right, let's do some more examples. Let's look at number 51. In this set, it says combine the radical expressions if possible. So you are given 3, or the cube root, sorry, of negative 16x to the fourth plus 5x cube root of 2x. And you are asked to combine these if possible. All right, so to do that, you have to simplify each term to its lowest form to see if it's even doable. So in this case, I need to think of 3 numbers that multiply 16. 2, 4, 8, Three, yeah, so I don't have three numbers, but I do have four numbers. I could do negative two, negative two, negative two, 2, 4, 8. Ooh. I'd have to do a random two here with that negative. So I could, hmm, let's think about it this way. Because I can't think of four numbers that would get that. I could think of four and four, two negative, no. Hmm. Ah. All right, so kind of thinking this in reverse. When I'm dealing with cube roots, when I have a negative, I know the answer is going to be negative when I simplify. So I'll just go ahead and pull that negative out so that at least here I won't get stopped from doing the work I need to do. Because now when I look at positive 16, and you only can do this if the index is 3. If the index is even, it's not even doable. So this would be 2, 2, 2, 2. So that's 2 times 2 is 4, and that gives you 16. But I can only pull out 3. So this would mean that this is now a negative 2 with a leftover of 2 on the inside. And then 3 goes into 4 one time with the remainder of 1. So then I'll read this one, and there's not much more I can do here either. Now, if this radical setup is exactly the same, then I actually can add these up. So negative 2x plus 5x. Remember, in this situation, we only can add the coefficient. So it's really negative 2 plus 5. So that gives me 3. And then the rest of the factors are just going to be written out as is. So now I get 3x to the cube root of 2x. And there's your result. All right, let's look at some more. So let's look at number 60. In this set, it says to simplify the following expression, writing your answer using the same notation as the original expression. Simplify the following expression, writing your answer using the same notation as the original expression. All right, so let's look into that. So we get the cube root, fourth root, and then x to the 36th. All right, so you can do this in a couple ways. One, you can do inside out, or you could simplify it. I think I'm gonna go inside out because I think I'll just keep it cleaner that way. In this situation, 4 goes into 36. I'll read the cube root. 4 goes into 36 9 times, so this does turn into x to the ninth. And then 3 goes into 9 3 times. Now, here is the situation. When you multiply these, 3 and 4, and you get 12, this is an even. So when it's an even index, you have to add this absolute value to it to make sure the original x is a positive. All right, it's the only time that this comes up. But when you try to just put x cubed in, I do apologize. It'll be the whole set, not just the x. Um, But if you try to put x cubed in, what happens is, remember, when you cube x, it can still be negative, right? So if I choose negative 2 to be my x, it won't work out because negative 2 cubed will give me negative 8 as a result, and I can't have a negative coming out of an even index. So if I plug in a negative 2 and I get negative 8, then the absolute value of that would be 8. So that's the thing you're going to caution yourself with if your index ends up being positive, I mean, even or odd. So in this case, since it was even, I just have to add the absolute value. So just watch out for that. But let's do some more examples other than that. So 63 is 81 to the 3/4. So it's the first time we're seeing it already in fraction form. All we got to do is just rewrite it. Remember, this is E over I. So I'm going to write the radical. I'm going to write the radicand. The exponent falls with it. and then the index is 4. All right, so this is 81 three times. Oop. My goal is to try to get 4 of the same number. So I know that 81 can break down into nines. When I do it this way, I see, whoa, there's 4 nines right there. So I know automatically a 9 can come out. I don't have 4 nines here, but I do know nines can break down into threes. I now have 4 threes, so I can write it one time. So 9 times 3 is 27. So I could do 81 to the third power, get a gigantic number, and then work it down, or just realize, all right, 81 cubed means that's 3 of them. Break down 81, get 4 of one number, and then see if you can keep breaking it down to the point where it makes the problem a lot easier to look at and to work with. All right, so get another one. So get number 67. This is x to the 1/5, y to the negative 2/3, x to the negative 3/5, and just y. All right. So again, I need to simplify these up first. So I have x to the 1/5 minus negative 3/5, and y, which is negative, is that 2/3, minus 1. Can't be scared of fractions in algebra. This is a lot of the work is fractions. Two negatives do make a positive. The denominators are the same, so it does make my life a little bit simpler. 1 plus 3 would just give me x to the 4/5. And then if you don't know, but a whole number, again, can be over 1. So if I just multiply by 3 to make it the same denominator, I can get negative 2/3 minus 3 over 3. And so negative 2 minus 3 actually gives me negative 5 over 3. And then because it's a negative, I know it goes to the bottom. So that's going to be x to the 4/5 and y to the 5/3. And hopefully it just stops there. Yeah, okay, I'm about to say, if we try to write this in radical form, which we can, it wouldn't do us any good because you wouldn't be able to actually simplify it any further. All right, last one. I think y'all have all the examples y'all need. 68 is 1,024 raised to the negative 2/5. All right, for starters, there's not much to simplify other than the fact that it's a negative exponent. So I'm just going to go ahead and get rid of that and say this is 1. Remember, if the numerator goes all to the denominator, there's always a 1 on top. So this would be 1,024 raised to the 2/5. Now I'm going to rewrite this as a radical. Remember, this is your x. So I write the radical, put the radicand in it. This is my exponent, so that's going to be a 2. And this is an index, which is a 5. So I need 5 of the same number. So I want to do that same process I did with the 81. So 1024 or 1,024 squared would be 1,024 twice. Now I'm going to try to think two numbers that multiply to 1,024. Honestly, I really don't know, so I am going to use a little bit of a calculator here. I think it will work. Let's see. So let's see. 1,024. If I had to guess, 30 squared is 900. 32 maybe? Ah, oh, I love that. All right, so 32 times 32 is 1,024. And then from there, I need 5. So now I go, all right, what multiplies to 32? 32 is definitely not a perfect square. But I know that 4 times 8 is. All right, so that would give me that. Those are still four fours and four eights, but I do now know that 8 can break down into 4 and 2. Man, before I go any further, this is what they're asking. Number 68. Okay. All right, so I got this twice. 32 times 32 is that. 4 times 8. Okay. Okay, so here we go. So then that means just cross them out. I get 5. So that's one, two, three, four, 5 fours. And then I got one, two, three. So I'm gonna have to break these down into twos. So then I got one, two, three, four, 5 twos right there. And then one, two, three, four, 5 twos right there. Okay, so that comes out nice and clean. So that leaves me with 4 times 2, which is 8 times 2, which is 16. So this actually ends up being 1/16. Again, the approach I went was just like in the 81. The goal is to get it down to prime factorizations, but a lot of time you can get your results before you even get down to prime factorizations. Because I could have easily written 2 15 times and then pulled 3 groups of 2. Nope, I lied. I could have written it 20 times and gotten 4 groups of 2 out and then did 2 times 2 times 2 times 2 to get 16. But I do try to get it before that point. That's just not one that's going to happen like that. All right. Other than that, that's pretty much all of your properties of radicals. I think that gives you a lot of good examples going into your homework. So if you end up needing more help, reach out and I'll by email and I'll definitely give you some more help. Other than that, I'll see you in the next video.